bundles on algebraic surfaces.
Thank you for inviting me in this conference. I want to talk about some topological structure or Donaldson invariant of the moduli space of stable vector bundles whose stability comes from the Gieseker-Maruyama on a fixed algebraic surface. Okay, so our aim in this talk is to study Donaldson theory and topology of moduli space of vector bundles satisfying certain notion of stability condition over a given algebraic surface. And roughly 3 items are under review and investigation. And first I have to apologize for that I have to use language of a sheaf. And sheaf is not so proper for a differential geometric language, but anyhow I have to use it. But also I have to, before that I introduce some bridge theory called Donaldson theory. So I hope you to understand the sheaf theory along this Donaldson theory. The first quarter consists of construction of Donaldson moduli of vector bundles, and also I have some construction of moduli space of sheaves in algebraic geometry category. Vector bundles roughly correspond to sheaves in algebraic geometry. And the second topic is Donaldson theory, and I will talk about the topology of moduli space of vector bundles over some toric surface. But our method is also applicable to more wider class of algebraic surfaces. And the final discussion is about some more discussion over of other types of surface like hyperkähler surface or some higher dimensional varieties. And because the introduction or motivation of this talk includes the definition of a moduli space of vector bundles and sheaves, so I will explain its motivation after the quick review of definitions and construction of moduli spaces. So I begin with a differential geometric construction of moduli space called Donaldson moduli. So I fix one smooth-oriented compact 4-manifold. So this means that X is differentiable, smoothly differentiable, and it has a fixed orientation, and it has compactness, and its dimension is 4. So I fix one complex differentiable vector bundle E of rank 2 on X, given surface X. This means that there is some kind of fibered space whose fiber is C2 because its length is 2. And I fix one Hermitian metric on E. This means that phi-wisely it's a Hermitian metric, right? And the Hermitian metric smoothly varies as X moves. And it always exists by partition of a unity property. And omega I of E means the space of smooth sections of E tensored with the I wedge product of exterior product of T dual. This means that iPhone valued iPhone valued sections of E, right? And I define D, the bold character is definition. D is a Hermitian connection. This means that it is a covariant derivative in the sense of the following. It satisfies the Leibniz rule. That's the meaning of covariant derivative. It looks like a derivation, usual derivation in smooth functions. And also it satisfies some metric compatibility with respect to the given Hermitian metric on E. And okay, I also introduced the notion irreducibility of a connection. So before irreducibility, I introduced D is reducible if it is a direct sum of 2 low dimensional connection. Low dimensional means it lies in low dimensional vector bundle. So in this case, we are dealing with rank 2 vector bundles. So D1 and D2 here are connections on rank 1 vector bundle. And otherwise we call D is a reducible connection. And we collect every connections, Hermitian connection, metric connections on E. Right? So it is a very huge space. It's infinite dimensional. And also, I delete, in AE, the space of Hermitian connections, I delete several redundant connections called reducible connections. So A star means a space of irreducible Hermitian connections. So still this is a huge space. This is an open set in AE. So therefore it's again infinite dimensional. So, but in E there are many AE, that's the space of irreducible Hermitian connections over A star E. There are many symmetries like which is given by gauge. So I collect all of them. This means that I would denote it as a calligraphic G, which denotes the gauge group. That is the set of smooth automorphism of E preserving the metric, Hermitian metric H. Right? So in diagram we can write it as the following. That's the canonical action on a given connection D with some gauge alpha. And then we quotient it because there are many symmetries. We divide by gauge group to modularize the connections in a genuine sense. So this quotient is denoted by BE, and B star is denoted by A star quotient by G. So now we have a kind of modular space, moduli space. Moduli space, this comes from German word, which means a collection of everything, a collection of some interest over our interest. So we have some moduli space of connections. But still, even if we quotienting out by gauge group, it's infinite dimensional. So we want to cut out some redundant connections by using Yang-Mills function. But before that, we consider a metric variation like this. Okay. So we collect out some connections satisfying certain curvature minimizing form. Say here FD is a curvature. This means the product of D itself. So we can integrate it after taking its norm over X. But here we need a metric on X, right? So now we generated some volume form over X, and then we can integrate the form on X, right? So whenever we fix a metric on X, we have some integration of a curvature, which is a non-negative number. So critical connections with respect to the above curvature integration function, which is sometimes Yang-Mills function, are called ASD connection, which is the abbreviation for anti-self-dual connections or self-dual connections. And these critical values are sufficient and important studying of our moduli space, and especially important in the Morse theory and four-dimensional Yang-Mills theory. And to find out these critical connections, I introduced some operator, important operator, which is called Hodge-Star operator. So Hodge-Star operator is such a linear operator on two forms on X. And I pick up one connection, then it is called ASD connection if the connection form after taking Hotchie star, it has a negative value of itself. Then we call D is a ASD connection. And Hotchie star FD equals plus FD, then I will call it self-Dirac connection. So abbreviatively, it's SD. So now we have a real moduli space. So this means, in other words, that's a energy minimizing. With respect to Yang-Mills connection, that's the energy minimizing connections on E over X. So still, we quotient it by gauge group G, then we easily can compute this G really acts on the space of ASD connection, and that's a subset of B star. That was the quotient of the space of connection space and the connections by gauge group. Now if G is calorimetric and omega is the Kähler form associated, then NGE, that was the space of connections modal gauge group, contains a closed subset of unstable connections. I have to define what stability is here. So D is stable if this inequality, artificial inequality, satisfies. So this is, if I take a subbundle of rank 1, because E is a rank 2 vector bundle, so non-trivial possibility of subbundle is just of rank 1 case. Right? So after taking wedge product of with omega, then it is a top form now. So we can integrate over X. And now we can compare these two values. Then if this inequality holds for all line subbundle or rank 1 subbundle, then it is called stable, mu stable, sometimes mu stable. So our definition of moduli space is Donaldson moduli space is a collection of stable ASD connection modal gauge group G. That's obviously a subgroup, subspace of NGE, the space of ASD connections modeled by G, and it is known that it is open set if non-empty. Okay, unfortunately, this moduli space, Donaldson moduli space, or if we collect all ASD connection modeled by G, that was denoted by NG, is not compact. So in many purposes, it is not so suitable for study, especially for explicit computation. So we have to compactify this moduli space. But according to the Uhlenbeck compactification, there is a natural topology compactifying this non-compact moduli space. Say it is there is a topology on this product space, okay, NG with first chunk class C1 and second chunk class C2 minus N, where C1 and C2 are chunk classes over originally given E. And Xn denotes the nth symmetric product. That's that parameterizes the n tuples of points over X. So I have to specify what convergence is in this topology. So more precisely, for a sequence of connections in NG, so the compact means the sequential compactness. Therefore, this implies there is some subsequence converges to some ASD connection, A infinity, I would denote it A infinity, whose first chunk class is 1, and the second chunk class is smaller by n. So in other interpretation, this means that E admits some delta function. Delta function is a Dirac delta function valued connection. So this closure, taking a closure in the bigger space and bigger ambient space of that, the disjointed union of products, we have now compact closure, which is called Uhlenbeck compactification, which we will use it. And there is a well-known theorem for perturbation of a generic metric of X. If we perturb generically the metric of X, then this, okay, I missed something, not M bar, just N is a smooth manifold. And now this M bar is now stratified by smooth strata whose maximal stratum has a codimension 4 in the compactification. Therefore, it has a fundamental class. That's a well-known theory, very well-known facts in, important facts in the Donaldson theory. But among introducing such a notion of connections, we meet some kind of bubbling in a Ulenbeck compactification. Bubbling means a Dirac delta valued connection. So we have to modify our theory a bit in terms of sections instead of a vector bundle itself. So that's the theory of sheaves. So now we introduce what a sheaf is on algebraic surface. So to introduce this, we have to fix on one form manifold, not just a smooth form manifold, but also it should be a projective surface. Projective surface means here surface means it's not real two-dimensional, but complex two-dimensional. Therefore, that's a real four-dimensional manifold. And projective surface means a compact complex surface in some given projective space CPN for some n. And by restricting the Fubini study metric of CPN, X is automatically scalar, and this scalar form is given by a first-term class, the one-on class of natural positive line bundle OX1, which is the restriction of a canonical line bundle, Hopf line bundle in CPN. And now we match what corresponds to vector bundle. So it corresponds to locally free sheaf in sheaf theoretic argument, sheaf theoretic language. A locally free sheaf E is a sheaf of algebraic section. So instead of a vector bundle, we consider dually it's a section. Okay. If I consider the vector space, its dual is a space of linear sections, right? So it's a dual argument in the linear algebra. So locally free sheaf is a sheaf of algebraic sections of algebraic vector bundle. Okay. So algebraic vector bundle is a vector bundle with algebraic structure. Algebraic structure means because vector bundle consists of a transition map. Therefore, if I say algebraic vector bundle, then its transition data comes from the algebraic map in whose value is GL. That's an algebraic group, so it makes sense. And coherent sheaf is a more wider class of locally free sheaves. It is a quotient of two locally free sheaves via sheaf homomorphism. So E1 and E2 are locally free sheaves, and coherent sheaf is given by always the quotient of this thing. So that's the co-corner of this sheaf homomorphism. And the torsion free means a coherent sheaf whose support is not lower dimensional than the dimension of X. This means that any section of E does not vanishing on an open dense subset vanishes on X entirely. Okay. There is also corresponding notion of Chern classes. Chern class is a topological invariant of vector bundles, but we can convert it into algebraic setting, which is called the Hilbert polynomial. Okay. So Hilbert polynomial is also I made a mistake here. PEN is a polynomial which is defined by holomorphic Euler characteristic of E tensor OX1 with tensor with n. Then n is an integer and n varies among integers. That becomes a polynomial. That's also well-known fact, even for any dimensional projective surface, any dimensional projective variety. And also we have to introduce some notion of scheme. That's the generalization of manifold in, that's the generalization of manifolds. A scheme which admits a singularity. The scheme is a generalized manifold in the sense that its local structure is a vanishing locus of some algebraic function. So it can have some singularities, right? So in other words, this means that if T is a scheme, implies the sheaf OT of algebraic functions, which is called structure sheaf, is defined in algebraic way. The sections of algebraic functions. Okay. And for a given scheme T flat family is a family of coherent sheaves on X product T, which is OT flat modules. This means that if I fix one element, each element of T, then restrict its fiber, then it has the same topological invariance encoded by this Hilbert polynomial. Okay, it corresponds to a smooth family in a differential geometry. Okay, so now we know what the projective variety is. That's a projective scheme with some additional structure, but we fix one projective variety with the ample line bundle. The ample line bundle was a restriction of Hopf line bundle in the CPN. So now we define the stability here. That's called Gieseker-Maruyama stability. And a coherent torsion-free sheaf E with Hilbert polynomial P is called stable, or respectively semi-stable if the similar thing in the Donaldson mu stability are whole are valid like this. If for any subsheaf of E, proper subsheaf E with the Hilbert polynomial PF, then this inequality holds. Then we say it is stable, or the inequality admits equality, then it is called semi-stable sheaf. And by this torsion-free coherent sheaf and fixed Hilbert polynomial, we can define some functor. Functor is it's like a function from a category to category, and moduli functor is a functor from a category of schemes that was denoted as bracket SCH bracket, and the right hand side is a category of sets, the ordinary sets, and the moduli functor is some function assigning T, where T is a scheme, and MT is a set of flat families of semi-stable torsion-free sheaves over a given surface X, given projective variety X, with a fixed topological data encoded by Hilbert polynomial P. And for practical uses, we divide it by equivalence, tilde. So tilde implies equivalence, some equivalence relation which identifies two sheaves up to isomorphism. Okay, I explain just below one line. So two T-flat sheaves are equivalent, which means that U1 with U1 are isomorphic after tensoring with some line bundle. So this notion is canonical for a family of sheaves. If I restrict one fiber, that's just the usual isomorphism of sheaves. So this corresponds to two vector bundles are isomorphic by gauge group. Okay. So to make a moduli space of sheaves, so I consider a large family of maps of this form. That's the sheaf homomorphisms with sufficiently negatively tensored and sufficiently large capital N. That implies the number of direct sums. And E is a semi-stable torsion-free sheaf with the Hilbert polynomial is given polynomial P, one fixed polynomial P. Then it is known that if we take a sufficiently large M0 and sufficiently large capital N, then every semi-stable torsion-free sheaf is incarnated as a surjection like this. So now we can parametrize all the semi-stable, right? And because PGLN action acts the domain of this map, and this quotient, this Q, I mean the Zariski closure of those set is acted by this PGLN action canonically. Therefore, we have a moduli space. This PGLN action indeed modularizes every possibility of symmetry in a space of sheaves, of stable sheaves with a fixed Hilbert polynomial P. So this is the moduli space of a semi-stable torsion-free sheaves on X with respect to the semi-stability is with respect to OX1 with given Hilbert polynomial P. So for short, I will call it moduli space of semi-stable sheaves. And similarly, we can define it, the sublocus MS, where S stands for the stable torsion-free sheaves. So MS is a subset of M. And furthermore, we can say that MS is an open subset of M. Okay. So the very well-known fact is M. I missed some explanation. M is a quotient space of PGLN, but we slosh it 2 times. That's the Hausdorffification of usual quotient space, because the usual quotient space is not Hausdorff, because there is an orbit collapsing. Therefore, we divide it by geometric invariant quotient, which is nothing but Hausdorffification in the category of isotropic geometry. Therefore, we obtained a compactification of this stable moduli space of stable sheaves. Yeah. And furthermore, we have some functorial interpretation in the category sense. So there is a unique natural transformation from functor, the moduli functor M, this flat M, to that functor, home functor. In the sense that whenever we have 2 arrows from a moduli functor, then there should be a unique function, unique functor from 2 functors. And this is given by from bold M to M prime. That's the, by definition, this corresponds to the cos moduli space. So, because M is a functor, but we can see it as a stack. So, stack is a kind of generalization of manifold, and M, if we see it as a stack, then the bold M, our moduli space, bold M, is a Hausdorffification. This is bold M is the Hausdorffification of a moduli stack or moduli functor. That's the same thing. have two moduli space. The first one was Donaldson moduli, which collect all of mu stable vector bundles, and also we can collect all mu stable. There is a canonical corresponding notion of mu stability on locally free shifts. So we have the moduli space of mu stable locally free shifts. So that is denoted by bold M, mu stable. So, and there is a canonical map between these two, which is called Hitchin-Kobayashi correspondence, proven by Donaldson. When X is surface, and for higher dimension, it is proven by Uhlenbeck, Jaeyoo. And also in this map, one can wonder if there is an extension of this Hitchin-Kobayashi correspondence map, and there is an answer. It is given by some called determinant line bundle on M. So this Hitchin-Kobayashi correspondence extended to an algebraic map. That's important. So this extension explains Uhlenbeck compactification is algebraic scheme, algebraic variety, because it has an algebraic map from M by a algebraic line bundle, which is called Morgan-Lee map. Okay, so we introduced the moduli space of vector bundles in two categories. The first one was differential geometry, which was called Donaldson moduli, and the second one was algebraic geometry moduli. The moduli space of semistable, the Gieseker-Maruyama semistable sheaves. So I explained some motivation because we now use some moduli space. So eventually we study some invariant on the moduli space, on the Donaldson moduli space, or algebraic geometry moduli space, and this moduli space is captured by so-called Donaldson invariant, or just we can study the usual topological space, say homology group over homology group. And Donaldson invariant was early 80s product, but in the late 80s, Witten interpolated as a correlation function in some four-dimensional supersymmetric Yang-Mills theory that was inspired many works in physics, string theory, and early 90s in a Seiberg-Witten paper, a very fundamental paper about the electromagnetic duality. They studied the Seiberg-Witten prepotential, which in Yang-Mills theory, which computes the period of hyperelliptic curves. There is some complicated function computing the period of hyperelliptic function. Yeah. And our gauge theoretic Yang-Mills theory, gauge Yang-Mills theory, and this period of hyperelliptic function, hyperelliptic curves, deeply related as late 90s, elicited by Moore and Witten. So they studied Seiberg-Witten prepotential and its relation to Donaldson invariant. In some sense, they are equivalent. That was the result proven by them physically, and more mathematically, Nekrasov find some concrete relation with the Seiberg-Witten prepotential and some partition function which is a Donaldson invariant over a moduli space, which called the Nekrasov partition function. That was the early 21st centuries. There was a very important topic. So this inspired many complicated computations in mathematical society. So, for instance, Necrasov Okunkov and Nakajima Yoshioka, and there are other real algebraists, for instance, Ettingov, and so on. They find out blow-up and wall-crossing formulas of the topology or Donaldson invariants of the moduli space in terms of Nekrasov partition function and Zeiberg-Witten prepotential. That's a recent that was a very recent progress. So, conclusion is that the Zeiberg-Witten prepotential has decomposed in two parts. The first one is the instanton part. That's our interest because it reads the topology or Donaldson invariant part of moduli space. The others are perturbation part. But this instant part is actually equivalent, contains equivalent data with Donaldson invariant of moduli space of vector bundles of various topological data. So this Zeiberg-Witten prepotential encodes very enormous data of topologies of moduli space of various topological data, prescribed topological data. That's the very big motivation of the Donaldson theory in the modern geometry. So now we define some Donaldson invariant on the moduli space. I can fix now a universal vector bundle on this product space X cross the moduli space, right? Because this is because we just fix one trivial the trivial extension of E on this product space and give a universal connection such that the fiber restriction is recovered into given D. So it is restricted by a fiber of D, then the connection becomes D, just D. That's called universal connection. So the pair of trivial extension with this universal connection is called universal vector bundle. So by this universal vector bundle, we can take a product in the slant product sense. So we can make a new map, say, from a homology space to cohomology space of moduli space by taking a slant product in the sense there. So minus 1 over 4 P1. P1 is a parametrizing class of E, cut product with the Poincare dual of alpha and its pullback. Okay, now this is some form, right? Form in the moduli space, and as far as the dimension, I mean the dimension of form meets, then we can integrate over the moduli space. Because it has, I said it has a fundamental class, so we can reintegrate it. If it is not matched to the top form, then it automatically 0, and otherwise it is invariant, symmetric invariant with respect to alpha 1 to alpha n. That's called Donaldson, sometimes Donaldson polynomial invariant. Okay. There is a K-theoretic counterpart of Donaldson invariant. So K-theory Donaldson invariant is somewhat functorial, especially for computation. So I have a 4-manifold X, or algebraic surface S, and S is a Noetherian scheme. Noetherian is not so important adjective, just a scheme. Consider just the schemes over C. And we consider S flat sheaf, calligraph E on the product space. that acts like a universal sheaf after all, but here just this is abstract setting. So, and then we denote P and Q are projections, corresponding projections as they are. And Kx denotes the K group. Sometimes it's a topological K group, but here with a holomorphic K group. It's a Grothendieck group, sometimes Grothendieck group of locally free sheaves on X. And we define some map from the K theory, K group of X to K group of S in the following sense. So we pull back an element of K group that's some coherent sheaf, right? Correspond to some coherent sheaf, a sequence of coherent sheaves to naturally the product space, and then tensor with the universal sheaf. This is not universal, but yeah, virtually that's a universal sheaf. And then we push forward P shriek. The P shriek is defined as an alternating sum of derived functor. And take a, now we have a alternating sum of sheaves. We can take now determinant. Then it's that's a line bundle over S. So that's an element of Picard group of S or K group of S. Now we let S Donaldson moduli over algebraic geometry moduli space. Then we have a corresponding proper notion of Donaldson invariant for one variable actually. So there is a relation between the classical Donaldson invariant we defined in the last page, and that's encoded in the K theory Donaldson invariant as a highest degree term, the coefficient of highest degree term. Okay, let us move to the concrete example, like Mn, that's the moduli space of semi-stable vector bundles of a given algebraic surface X with rank 2, first chunk class 0, and the second chunk class the positive number n, non-negative number n. And usually the instanton generating function is defined as a kind of depth function summing over all second chunk classes of holomorphic Euler characteristic of line bundle by Donaldson mu map. Or sometimes we can replace that calligraphic O into just a locally constant sheaf to encode topology of Mn. Basically, that's that causes no confusion. But there is an obstacles like to compute this invariant, because this formula acts idealistically for smooth moduli space. But we can replace this non-smoothness into perfect obstruction theory in a derived category, or also we have another problem like the existence of fundamental class, and it is a replacement, well-known replacement by variant, which is called virtual fundamental class. Okay, so our interest is to compute that instanton generating function, which includes the holomorphic Euler characteristic over just the topological Euler characteristic of moduli space. Okay. But for the proof, for those computations, because our moduli space is very high dimension or very high dimension, so it is very difficult. So basically, there is only unique method to compute it. That's the torus action. Okay, but so because there is an obstacle of a smoothness of moduli space, and in computation of topology or Donaldson invariant, so we need some another type of, some some kind of generalization of moduli space. That's called moduli space of parabolic structure. So before this moduli space of parabolic structure, the moduli space was collection of sheaves or vector bundles. But from here, that's the moduli space of some vector bundles with some additional map, say frame. So that's the pair, parabolic structure, eventually pair, which is called the framed sheaf. So E is a sheaf on given algebraic surface X, and alpha is a map from E to D. Okay? I will assume this alpha is non-zero and D is a fixed sheaf, but E can vary to modularize every such sheaves. And because we introduce this kind of extended notion of sheaf, we have to introduce an extended notion of a topological invariant. That's encoded by this extended Hilbert polynomial. So Hilbert polynomial, this map is encoded by a polynomial like that, but one should note that there is an additional term, epsilon alpha delta. Delta is a delta is a Dirac delta function, and the epsilon is defined as there. Because we need some additivity of sequence of sheaves, framed sheaves, so we can study in a similar sense of the study of sheaves. We can define what exact sequences in a category of framed sheaves in the commutative sense, like that. And yeah, the final sentence is about the additivity of this Hilbert scheme. That's what we want to say. And so the conclusion is that this extended Hilbert polynomial acts like the ordinary Hilbert polynomial. And two framed sheaves, we have to identify two different or possibly different framed sheaves in the sense of there. And also we can define the stability of pairs, the framed sheaves, like that. So this is slightly different from the ordinary stability because we have some additional map, alpha, right? So if I have E alpha, then its subsheaf, say framed subsheaf, is a pair of F and alpha restriction. Alpha restriction is just a restriction map to F because F is a subsheaf E, subsheaf of AE, right? So now we can compare the normalized Hilbert polynomial, those two, and in the similar way of ordinary Hilbert stability case, I can compare those two Hilbert polynomials. So if this inequality satisfies for all non-trivial proper framed subsheaf, then I'll call it as a parabolic structure. So there is a abstract generalization of this kind of discussion. The conclusion is that if I take a sufficiently small delta, I'm sorry, I missed something. Delta was just a small positive real number. I said some minutes ago. I said it's a Dirac delta function. I missed it. So if I fix a Hilbert polynomial, extended Hilbert polynomial, and I can consider framed sheaf, semi-stable framed sheaf, or parabolic structures, then there is always a phi moduli space eventually. So this is a phi moduli space means we don't need a Hausdorffification. So this is a genuinely obvious space of moduli space. So this is, we can see this encodes a moduli data without loss of orbit closing. Okay, so why do I consider this kind of complicated methods? Because this provides a desingularization of ordinary moduli space, because ordinary moduli space can have a singularity. So I define the moduli space of parabolic structures, pair of E and alpha, and here D is fixed as a CP. That's the coherent shift supported at only one point P. That's usually called the skyscraper shift because it looks like a skyscraper. With its topological data is given as rank is 4, and first chunk class is 0, and second chunk class is 4n. And I fix a given base manifold as a toric surface. Actually, at this stage, toric is not so important because we can make a moduli space of this kind in various surface or various manifold according to the Huybrechts and Lenz result. And this parabolic moduli space, after moving P suitably, then this parabolic moduli space parametrizes semi-stable sheaves without orbit collapsing. That's the phi moduli space. And we consider the subspace of this parabolic moduli space. Parabolic moduli space is actually almost, that's in algebraic geometry language, that's a birational to the ordinary moduli space of sheaves with rank 4, chunk class 0, second chunk class 4n. So that's a too big space compared to our interest of moduli space of rank 2 sheaves. That's the doubled, right? So we consider it's a subspace. This is still moduli space of something, and this I will denote it as a MS. This means the moduli space parameterized in a family of parabolic structure. But important thing is that its endomorphism, is dimension 4. Okay. Because E has a rank 4, the endomorphism 4 is quite important, has quite important meaning. The endomorphism of E freely acts on its every fiber. That's the very important interpretation. And I attach the subscript S, means that universal sheaf E is has an endomorphism sheaf, is an Asmaya algebra sheaf. I will not explain here. And now we have a projective desingularization of M. So we have an ordinary moduli space of M. This is because there is a vanishing obstruction theory, and we mimic it even to X is hyperkähler surface. And originally, for when X is a compact Riemann surface, so complex dimension 1 case, was done by Seshadri and Mumford. And for higher dimension, because the obstruction theory appears, so there is a big difficulty usually. And we want to say something about this resolution. I mean, the resolution implies desingularization. And if I restrict some dense open set, say stable locus, the moduli space of stable vector, stable sheaves, then this is nothing but just the isomorphism. So there's nothing new on the stable locus, and its isomorphism is by just taking double. If I take a semi-stable sheaf F, then it corresponds to the F product F. So you can read this desingularization and in a very interesting way, because E is a stable sheaf with rank 2, but because F is a stable sheaf, so its endomorphism group has just dimension 1, so it cannot perturb their fiber. But F cross F has a rank 4, and the endomorphism has a rank 4. dimension 4. There, and we can see that the endomorphism, global endomorphism permutes the fiber. So that's the very important observation. And then we talk about some properties of outside of a stable locus. That's the essentially important part. So usually in algebraic geometry, this is called exceptional locus because it is a locus where pi is not isomorphism. So outside of isomorphism locus, there are three types of sheaves like that. The first type is first type or second type or third type are all expressed as extension spaces of ideal sheaves. So important thing is that the conclusion is that we can compute the endomorphism group of each fiber. So you can see that every one of them, okay, in the stable locus, the endomorphism group was M2, the 2x2 matrix. That was a semi-simple algebra. But on the other hand, the other fibers, the endomorphism group was isomorphic to solvable algebra. That's a very big change, right? Important change. So because of this change, we can perform some computation for a Donaldson invariant of a topology. So I expected there is some shortage of time, but I briefly what is going on here. So if I take a section of this endomorphism algebra, endomorphism sheaf properly, then it gives a total section on E. Therefore, we can compute the equivalent K theory on this sheaf E. Yeah, using a residue formula. Okay, maybe it consumes too much time to be precise all of these terms. So I skip here. Basically, so what is going on? I would tell it. Okay. So in a toric surface or arbitrary surface, in arbitrary surface there is no computational method. And toric surface there is a computational method because toric surface has a torus section. So we can contract by some natural torus section to a simpler way by residue formula. But otherwise there is no hope. But this is progressive work. I think if I take a different torus section given by a section, then it has some distinctive fixed point of classical results of Konsevich or Nakajima or some other persons. So yeah, it's like that. So there is a computational result by Nakajima Yoshioka for some framed moduli space. The framed moduli space, some extended moduli space, but anyhow, by this we can compute the topology of the ordinary moduli space, and also using very different method by cell decomposition, we can compute a very simple case of moduli space of vector bundles over sheaves over K3, the hyperkähler surface. That's the Euler characteristic is that number 1769.4, and yeah, that's the end of my talk. And there is some prospect of this my talk. It's related not just at 4-dimensional but also 6-dimensional. There is a very big surprise in 6-dimensional theory, the 6-dimensional Donaldson-Thomas theory, conjectured by Konsevich and Soivelman in the last year and this year, and also Sekoty and Baffa in physics. And this is some Donaldson invariant or topology of moduli space of sheaves or vector bundles over a threefold, complex threefold. And this was conjecturally very related. There has been a Donaldson-Thomas invariant and Pandari-Thomas invariant and central invariants on the Calabi-Yau manifolds, and some partially their explicit relations in terms of stability. That's the generalization of our stability, which is once defined in the lecture, called Bridgeland stability, or in physics, the Douglas stability was explicit. And for more grand picture, there is a Donaldson-Thomas and Gromov-Witten correspondence, which conjecturally there is some equivalence between generating function in Chern-Simon theory and Gromov-Witten theory. And Chern-Simon theory is related to our discussion of moduli space of vector bundles. So I stop here. Thank you.
Are there any questions?